Okay, a couple announcements. Your exam 2A. So you have two exams for Module 2. 2A is going to be on mass spec and IR. That will open today and close tomorrow. There's also an infrared bonus that's also open in zip grade. So there was an announcement last week about that. That will close tomorrow at 12:15 as well. And so today we're going to start on infrared spectroscopy. So I'm going to give you sort of the basics, a little bit of the theory and how you interpret the spectra. There's two resources in Canvas that you should go through. One of them is a static PowerPoint. You can just click through. It shows you what the functional groups look like. The other one's a screencast where I'm talking through that PowerPoint. And I think the screencast has little animations or movies. So when you're looking through it, you'll see sort of a simulated IR spectrum. The static PowerPoint might have those as well. So when you open that file and you hover over that little movie, I think you can click play on it. And it'll show you what we're talking about today. So within that file, again, there's the different functional groups that we talked about. And what I'll show you in class today is how you want to interpret these spectra. Really, the thing with IR, it's visual. So you're looking for the way signals look to associate them with a functional group. And if a signal is absent, you can rule out that functional group being present. So that's the key part. Any questions before we get going? So the question that we had, from mass spec was that some of these heteroatoms show a unique signature that, indicate that element is present in the molecular formula. But oxygen, which is one of the most common elements in organic chemistry, it's ambiguous if it's present just based on the mass spec data. And to increase our confidence level in determining if an oxygen functional group is present, we're going to look at infrared spectroscopy. So because this is spectroscopy now, we're dealing with light and how light interacts with matter. If you're going to take the MCAT or pre-pharm or vet exams or anything like that, spectroscopy is pretty important for you. It's an imaging technique. So in this class, we're imaging molecules. In health professions, you're imaging the human body or an animal, and you're getting information from that. So IR is really used to identify functional groups. So remember that a functional group is just a discrete collection of elements with a certain bonding pattern that can exist within the molecule. And to just give you a preview of what this is, say we have the alcohol functional group. And I'm going to abbreviate the alcohol as ROH. So R is the rest of the molecule, and the OH is the hydroxyl group of the alcohol. We know that oxygen has 2 bonds, 2 lone pairs. And based on the difference in electronegativity of the elements, we can say that the oxygen will be delta minus and the hydrogen delta plus. Once we do that, we can formalize it in another way called the dipole moment. So because the oxygen is delta minus, we would point the bond dipole in that direction. So the delta plus, the plus side of that sort of arrow starts there, and the arrowhead points to the minus. So that would be a dipole. And that's important for IR because what's happening is in infrared, that light is exciting that dipole. And so if we think of the OH bond as something that can move, like the movement of a spring, the light's going to excite that dipole and make it move. And the instrument will detect that as a response. And so that's the signal that we see. So really what we're looking for is that's how the electronegativity trend looks in the periodic table. We're looking for bonds that have, a significant dipole difference. And then that will lead to the IR response. So as we run through this, we'll focus on the different regions of the IR spectrum. What are we looking for? What is each region telling us? So I'm going to throw this out here, and then I'm going to pick a little bit of some information out, and then we're going to go back and sort of analyze the spectrum itself. But this is what an infrared spectrum looks like. On the x-axis, the unit is called wave numbers. And so wave numbers are typically reported in inverse centimeters. So that what that means is 1 over centimeters. And that's the wavelength of light at which the excitation occurs. On the y-axis is either transmittance or percent transmittance. So getting back to the x-axis here, on the left side you see that's 4,000 wave numbers, and on the right side is about 500. So when we read these, we're typically reading them from left to right, and then we'll assign regions where certain functional groups occur. On the y-axis, there's 100% and then 0%. So 100% transmittance means all of the light is passing through the sample and detected. So it's like this. You can see that green light. So that would be 100% transmittance. Now if my hand were the sample, and I put my hand in front of it, so now that's 0%. So my hand is stopping the light from getting to the detector. So if we're reading from left to right here, so if we follow that, that's 100%. And then it's going to get to a functional group where it starts to dip down. That means that light is being absorbed by some functional group in that region. And you can see the region, spans 3,500 wave numbers. So the functional groups are in different spots along that x-axis. So we left off last time talking about, the parent ion having this mass to charge, and if it was 72, we did some assumptions through, these intuitive techniques of, 72 has to contain CNH If we divide that by 12, that would give us the maximum number of carbons. But what about this situation with oxygen? So we have that piece of data, 72, and then on this particular spectrum, the main signal that we're going to pull out of this is this one indicated at 1730. So 1730 wave numbers. So again, up here, that's 100% transmittance. And then you see it starts to dip down. It spans some certain wave numbers, and then it goes back up. So that's a signal. And that particular signal, the way it looks in that region, belongs to a carbonyl group. So it's my teaching philosophy that for this class, I'm not going to go into the mathematics of this, like why that signal occurs there, why it has that shape, the intensity, the span of wave numbers. Really, it's very qualitative, and you're looking at the region and how the shapes appear. So I would classify that as a strong signal, because when you draw the line over to the y-axis, you know, we're at about something like 5 or 10% transmittance. So it goes from 100 almost down to 0, so that's pretty strong. And so once we accept that signal's a carbonyl, we can start thinking more about how does that impact the number 72. We can see already there's 1 degree of unsaturation due to the pi bond. What it's also telling us is there's at least 1 oxygen. So we can take 72 minus 16, and the rest of that is a carbon-hydrogen count. Then we can make further deductions while there's a degree of unsaturation, so that needs to be accounted for in the math that we figure out. Any questions so far? So we're going to return to this spectrum probably on Wednesday. But right now what we're going to go through is how to think about functional groups and where they lie on the x-axis. So in Module 1, we spent time talking about how do we communicate structure. So there's the actual drawing of the structure, and then we have these different words and abbreviations for the functional groups. So this question is asking, what functional groups have a heteroatom bonded to hydrogen? So I would abbreviate the heteroatom as X. And then what it's asking you is which functional groups have XH? Any guesses? Huh? Thought I heard the right answer. What? D. Yeah, D's correct. So we have OH. So I'm just going to draw that squiggle. Primary amide has NH2. Secondary amine and then a carboxylic acid as OH. So those are all functional groups that have a heteroatom sigma bonded to a hydrogen. In choice A, an ester does not. In choice B, a tertiary amine does not. And then in choice C, a tertiary amide does not. What functional groups have a triple bond? So A, we have an alkyne and a nitrile. So carbon-carbon triple bond is an alkyne, carbon-nitrogen triple bond is a nitrile. So B and C both have alkene, and we know that that's a carbon-carbon double bond. D has alkane, that's a carbon-carbon sigma bond. So again, the point of this exercise is when you see that functional group name, what does it look like chemically? What's the bonding pattern? What functional groups have a carbon-oxygen double bond that is also called a carbonyl group? So C. So the aldehyde has the carbonyl at the terminal carbon of the chain. The ester has a carbonyl that's bonded, sigma bonded to some other oxygen. And then the ketone, the carbonyl is on an internal carbon of the chain. So A, the nitrile, that's the carbon-nitrogen triple bond. Alcohol is the OH. And then D, amine, is nitrogen sigma bonded to either carbon or hydrogen. So what functional groups have a carbon-oxygen double bond with an additional oxygen atom bonded to that carbon? So B as in boy. So an anhydride, that's the one that has two carbonyl groups. Carboxylic acid, that other oxygens bonded to hydrogen, and then ester, the oxygens bonded to another carbon. For A, the amide has a nitrogen bonded to carbonyl. For C, you have a chlorine atom bonded to the carbonyl. And then for D, none of these would be correct. So the aldehyde has that H, the amide has a nitrogen, and the ketone has two carbons. So now we're looking at carbonyl bonded to nitrogen. What was the name of that? So amide. So the amide must have that collection of elements with that bonding pattern. So we're going to use the abbreviation R for like everything else in the molecule. And then you see the functional group names here in the columns. And it's asking you of the choices, which one represents the bonding pattern for that name. So if we just look at the alcohol column, we can eliminate B and D. So we're just looking for OH. One thing I want to point out for this, when that OH is bonded to a carbonyl, that's called a carboxylic acid. And again, that is different from an alcohol. So we have B and C, and the next column is amine. So in choice A, that is representing an amide. So that's how you would expand out, that collection of letters and numbers into a structure. So that's out. So C would be the correct response. And then as we saw, again, the carboxylic acid is a carbonyl bonded to an OH. So now we have amide, alkyl chloride, and acid chloride. We know that the amide must contain a carbonyl. So that eliminates B and D. This nomenclature here, CO, this is where it can get confusing, so you have to know the Lewis dot. When you expand that out, that CO means carbonyl. So alkyl chloride, that just means a carbon atom sigma bonded to a chlorine. So in choice C, we see that CO, that means carbonyl, so that's out. So A would be the correct response. So alkyl chloride is this, acid chloride is that, has the carbonyl. So what is the point of all these questions? Basically, the way we went through them, we were looking at the different bonding patterns of the functional groups that we've learned so far. And they're presented to you in the order of reading the spectrum from left to right. So the first region, what I'm calling single bond, so that's CH, NH, and OH. The second region contains triple bonds, so alkynes and nitriles. And the third region contains double bonds, carbon-carbon, so those are alkenes, and carbon-oxygen double bonds, those are carbonyls. And these are, as we saw in those questions, there's lots of them, right? We have a carboxylic acid, we have an ester, aldehyde, ketone, amide, acid chloride, and hydride. There's a lot of functional groups with carbonyls. So within that, when you're looking at that specific region, that signal for the carbonyl will either occur in a specific region or it will look a certain way. And so it's like a matching game. You know, when you're a kid, you're sort of matching the shape to a name. That's really what we're doing here. So when we read this spectrum left to right, we're looking at those three regions. Is a signal there? If it is, what functional group does it look like? If it's not there, then you can eliminate it from being a possibility within the molecular formula. So here are those regions defined structurally. And again, imagine we're reading this. You know, on the left, we said there was 4,000 wave numbers. And then as we move right, region 2 is about 24 to 2,200. And then region 3 is 1,800 to about 1,600. The spectrum goes to 500, but really anything below 1,500 we just ignore because then it gets a bit too complicated for us. Within region 1, we have alkane CH stretching. So I'm going to use that word stretching, and I'll define it a little bit later. So that's sp3 hybridized carbon H. We have alkene sp2 hybridized carbon H. And then we have a certain type of alkyne sp hybridized carbon H. Amine, if it's primary or secondary, we have NH, and then alcohols will always have OH. So carboxylic acids would be in here as well. You would see that OH. For region 2, that's the triple bond stretch. We have sp hybridized carbon nitrogen, that triple bond. For alkyne, it has to be that specific type of alkyne, terminal, where the triple bond is at the end of the chain. If the triple bond is internal, you do not really see a signal because, as I said, what the instrument is doing, it's looking at the difference in electronegativity between the two elements of the bond. Since they're both carbon that are bonded to carbon, you don't really have a big difference. So the light that shines through it is not really seeing anything. But for the terminal one, you have carbon and H. And so that makes this triple bond different than this triple bond because you have carbon and carbon. And then region 3 are all the carbonyl containing functional groups. So aldehyde, ketone, carboxylic acid, ester, anhydride, acid chloride, primary amide, secondary amide, tertiary amide. So if you're looking at a spectrum and you see nothing significant between 1,800 and 1,600, you can confidently say there is no carbonyl group in that molecule. If you do see a signal there, then you got to look, well, it could be how many is there? Like 9 functional groups. Which one of those 9 can it be? And that's when you have to start making these connections to other pieces of data. So for example, in the mass spec, we learned about chlorine isotopes. That can give you a hint if it's chlorine. We learned about the odd mass rule. If the mass is odd, there's an odd number of nitrogens, so you might have an amide. So you have to start making these connections to build confidence into what you're going to claim as a structure. Any questions? So I'm sure that you've sort of talked about this concept in general chemistry. If you've taken physics, you've probably talked about it. I think every STEM course introduces the electromagnetic spectrum for some purpose throughout, their courses. So this is the electromagnetic spectrum. So really, if you look up and you see these lights, that's what we consider like light. But the electromagnetic spectrum in general is light. So along that spectrum, what differs is the wavelength of light. So if you have like a really long wavelength or a really short wavelength. Let's go ahead and look at this starting from the right. So if I start here, and I put sort of 2 points. So those crests of that wave, that would be considered the length, the wavelength. So that would be a really long wavelength. Then if you look at the arrow right here on the bottom, that's low energy. So a longer wavelength has lower energy. As you decrease the wavelength, the energy gets higher. So you can see the names of the different types of light on the spectrum. So radio waves, if you still listen to AM, FM radio, the stuff that's like broadcast for free, those are really long wavelengths. They're not terribly energetic because, you can listen to them and they're not like doing any harm to your body. Microwaves, now the wavelength's getting shorter. So when you throw in your popcorn or your Hot Pocket into the dorm microwave, what is the microwave doing to it? If you put it in cold, like when you grab it, how does it feel? It feels hot. And so obviously the microwaves are doing something to it. Really what they're doing is heating up the water. So they're making the water move a little bit faster and your food gets hotter. So microwaves to IR, that's what we're going to talk about, infrared. And right here in this little bit right there, that's expanded down to here, that's the visible region. That's what we see. We perceive color as humans. In organic chemistry 2, we'll go in more in depth about how things get color and how we perceive them. Beyond that is UV, ultraviolet. Then X-rays. So if you go to the dentist, they'll take X-rays of your teeth. That's higher energy. And then cosmic and gamma rays, those are things that stars produce. So those are really high energy. So like the James Webb Space Telescope can detect those things from light years away, right? So it has to be really high energy if it's traveling so far. What you'll notice below each of those is these things like nuclear spin transitions rotational motions, bond vibrations, electronic transitions. That's the impact of that energy on the molecule or the element or atom. So within infrared spectroscopy, we're talking about bond vibration. And the easiest way to think about that is the motion of a spring. So you have a bond that consists of two elements, and they're connected by a spring. The spring is really the dipole that we're talking about. And because these different wavelengths of light have different energy, in IR, the IR light is affecting that spring. We'll talk about radio waves when we get into nuclear magnetic resonance. So that type of wavelength interacts with the molecule in a different way. So to really understand what the IR spectrum is telling us, let's just revisit what a bond is. So as I said, you have, this element, this atom, then you have another one. So we normally draw a line, but that's not the best way to think about what a bond is. The best way to think about it is a coiled piece of metal called a spring. So when we're reading this graph here, this is a common graph to describe how bonds look. On the x-axis, that's the distance in angstroms between the two elements or atoms. So if we look all the way to the right, we can see this hydrogen atom and this one in blue and yellow. They're really far apart. They exist, but they don't know the other one exists. And if you're reading from right to left, you're going down this curve. And the distance between them is decreasing. So you have these electrons that then become attracted to one another. So each hydrogen atom is supplying an electron. They're going to get to a point or a distance where they want to form a bond because two electrons make a bond. So they get closer and closer and closer. And then they end up in this well here. And there's this line that says average bond distance. So that's what, when we're thinking of a bond as being static, like there's no change in motion, that's that distance, the average distance of how that spring moves. But since it's a well, you have the atoms moving apart, and then they're compressing together. So within that well, there's constant motion of those atoms like this. If they get too close, notice what happens on the y-axis. If they start getting too close, they're physically overlapping with one another, and then the energy skyrockets. So within the average bond distance, on the y-axis, there's a bond energy. The energy required to break that bond. So when they're really far apart, they're existing, but they're not aware of each other. They come closer and closer together. They form a bond. If they get too close, there's repulsion, and the energy gets greater and greater. So I always ask this, does anyone know who that is? This is everyone's okay, it's Bob Ross, and so this is the happy place for those two elements to form a bond. So they're not lonely, they're not far apart, they're not too close together where it's high energy and they're stressed. But the key thing to keep in mind is even though we're representing, H2 like that, those atoms are constantly moving. So this slide used to be a video. It's no longer a video because I'm teaching from a PDF here, but if the bonds are springs that can move, that's called a vibration. And in infrared spectroscopy, there's different types of vibrations. And a word that's used is stretching. So this first example here is symmetric stretching. Now imagine that I'm a carbon atom and my hands are hydrogen atoms. So I'm a CH2 group. So symmetric stretching means that it's going like this. Both are moving in the same direction at the same time. Asymmetric stretching is now they're sort of like the pistons in your car. They're moving in opposite directions. So these are called vibrational modes. And in addition to the region on the x-axis where these things occur, that's why you see a lot of jaggedness to these peaks. Because from the uniqueness of CH groups, hydrogen sets, you have all these different hydrogen sets. Some of them are doing this, some of them are doing this. They all overlap in one region, and the peaks look really jagged. Wagging, what is wagging? I think wagging is, so like stretching, if I'm sort of in plane like this, wagging would be like out of plane. So like I'm the plane with the carbon, I'm doing either symmetric or asymmetric, but wagging, it's coming out of the plane. So twisting, you're doing your oblique ab stretches here like this, it's twisting. Now, again, keep in mind that all of these, since they're different vibrational modes, have different energies. Because on that bond curve, when the light's hitting it, it's going to excite it in a different way. So that the hydrogen atoms can do scissoring motion, so you're cutting the piece of paper like that. And then rocking, I think you're sort of like wagging, but you're rocking out at your favorite disco. You go to discos, clubs, whatever they're called nowadays. So all of those different motions are possible with IR light because those bonds are acting as springs. And as I said, we're not going to get into the mathematics of this because it's not going to inform us for the purpose of this course. We just want to know, how do these signals look and where do they fall? So here's an overlay of the three regions we're looking at. We said that the y-axis was the transmittance or percent transmittance. That just means how are the numbers going to look. So transmittance, your scale as shown here would be 1 to 0. Percent would be 100 to 0. And then the x-axis is in wave numbers. So again, the percent transmittance or transmittance is the amount of light that's passing through. So as the light is scanning and it hits a functional group, it's exciting it. Another way to think about that is the functional group is absorbing that light. So from 100%, it's now dipping down, and that's the signal. So region 1 were the functional groups with XH. so CH, OH, NH. Region 2, triple bonds, so alkynes, nitriles. N3 was azide. So that's a nitrogen-nitrogen triple bond. And then region 3 were your carbonyls primarily. Notice up there it says carbon-nitrogen double bond and carbon-carbon double bond. Those will most likely fall lower than 1600. And that's really our cutoff. I have this region 4 here which says fingerprint. When you get into there, the IR spectra are a little bit more difficult to interpret, so we generally just ignore them. So the wave number on the x-axis is where you're seeing that functional group. It's generally reported as one number, so that the closest that signal is to the x-axis, that's the number that's being reported. And as it says there, we're really reading from left to right. Region 1, then region 2, then region 3. Is something there, yes or no? And then we can sort of, use a flow chart to help us determine what functional groups are present. So in terms of the regions and their wave numbers here, region 1 is about 36 to 2700. Those were the XH stretching. So think about the functional groups that have that. So OH, NH, CH. It says alkane, but alkene and alkynes occur there as well. So every molecule we've seen so far has CH. So you're always going to see something there. So it's really not terribly useful. Region 2 was 2500 to 2100. That was our triple bond groups. So alkyne, azide, and nitrile. Region 3, 1850 to 1600, are double bond stretching. So mainly carbonyls. CN double bonds are called imines. CC double bonds are called alkenes, but really we're looking for carbonyls. Region 4 in purple was the fingerprint region. That's anything below 1500. And that really, the reason that's so complicated is it's a lot of the sigma bonds that are present. So CC sigma bonds, CO, CN, everything's down there, and it can get pretty complicated. And it's not worth our time trying to figure out any structural information from that. We have other means of doing that are a little bit more straightforward. So we utilize the IR to determine if functional groups are present. So you see this signal, or if they're absent, that region has no signal at all. So all molecules have CH stretching in region 1. So again, you'll just have to look at a lot of these to say, okay, that's the CH stuff. Is anything else there that looks like OH or NH? So really you go to region 2, is there anything there, yes or no? And then the same for region 3. So you're developing an intuition and you're applying logic to see what bonding patterns could be present in a molecular formula that I'm giving or a parent mass. These tables are really just ripped from your textbook. I guess the way they're organized is according to the kind of the region here. They're really just meant for confirmation. You know, see, these are in column 1, those are the different bond types we've learned. Column 2 is bond energy. We'll talk more about bond energies in module 3. But for now, it just gives you an idea of how the light is exciting that specific type of bond. The third column is the range that you're looking for in the region in column 4 there. So signal intensity, as I said, you know, when you're looking at 100%, strong means like it's dipping pretty far down. Then you have this sort of shape as well. So what I mean by shape, so I would say that's a sharp peak. Something that's broad would really span a lot of wave numbers. So a sharp peak is going down, there's a point, and it's going back up. Broad, it's sort of going down, it passes a lot of wave numbers, and then it curves back up. So visually, that's what you're looking for. This is just the same information presented to you in terms of the names of the functional groups, and I believe they're listed in alphabetical order. So you can just refer back to this as you know, confirmation is it there or not there? Questions? Any more questions? So if you haven't got one of these sheets, could you grab one? Everyone got one? Anybody else? So if you could print your name, sign your name, and fill in your USMID, fill in the bubbles. So we have 15 spectra we'll look at. So I'll give you about a minute and a half for each one before I go to the next one. So what I want you to do is look at the spectra, see if you can figure out what functional group is present. So when we're done, you'll hand in to me one sheet and one sheet only. And every answer you get correct, I'll give you 1 bonus point for. You can chat with your neighbors, use any resources you want, but please make sure you have your ID on there correct, because that's what's going to associate it with your zip grade. Yep. So at the end, this is the important part for me. You just need to come down and hand me one sheet direction. So the question's all the same. What functional group is present in the IR spectrum? We'll go ahead and start. Give you a minute and a half. Ten seconds. Next spectrum. Ten seconds. Next spectrum. Ten seconds. Next spectrum.
10 seconds. Next spectrum. Ten seconds. Next spectrum. Ten seconds. Next spectrum. Ten seconds. Next spectrum. 10 seconds. Next spectrum. Ten 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 seconds. Last spectrum. Okay, we're about out of time. So if you can bring your sheets down here and hand in me one sheet per person, please.